Okay, so this one about different form principle space. Within cohomology, cohomology is simple. What total principle is of one. Yeah, I want to look at the equal-forms. To characterize this G E I C is the one about map 30. It's a trivial inject from back from directed. Say form. Okay. Now Rx on Rx on R2 by addition of the second coordinate. So this is a principal R bundle. Yeah. So R applied to xy is xy plus R. Okay, that's the action. And so you have a principal R bundle, and it looks like this. Now, so omega, a one form on omega, a one form on R2, a one form on R2 it's a linear combination of dx and dy. Okay, so it is going to be fxy dx plus gxy dy. And the basic one forms they are pullbacks, okay, of some function hx times dx. And so this, now the pullback of a product is a product of the pullback. Okay, so it's going to be the pullback of hx. Okay, the pullback of dx is dx. Okay, so you see that one form is basic. First of all, if it has no dy term, and then this f cannot involve y. This must be a function of x alone. Okay? Yeah. So let's see. So we can say that omega is f dx plus g dy is basic if and only if, okay? So omega has no dy term, and f of xy does not depend on y. Okay? Okay, now I'm going to rewrite this condition using interior multiplication and the Lie derivative. So let's first calculate the Lie derivative, the interior multiplication of y with respect to ddy. Okay? So I ddy of f dx plus g dy. Okay. Yeah, that's right? Yeah. And, okay, so what can you do with this f? interior multiplication is f linear, so that f just comes out. This is f I d dx, d dy, dx plus g I d dy, dy. Okay? And now, how do you calculate this? What is that? Why is it 0? Yeah. Yeah, right. It's 0 because I d dy. Right. Of course. Yeah. You just apply dx to d dy, right? That's the definition. And then this is d dy x. Okay. So that's 0. Yeah. And then I d dy dy. Okay, what is this? That's dy applied to d dy. And that's dy dy. That's the definition of df, right? D of something. And so 1. And so this is going to give us g. Okay? So because. And so to say that there's no dy term is equivalent to saying that the interior multiplication with I d dy is 0. Okay? Okay. And let's also calculate the Lie derivative with respect to d dy. Okay. F dx plus g dy. Okay. Okay, now you can't just take f and g out because the Lie derivative is not f linear. But you can apply the product rule. It's a derivation, so you're going to get L d dy f dx plus f L d dy dx, okay, plus L d dy g dy plus g L d dy dy. Okay. And the Lie derivative of a function is just the derivative. So this is df dy dx. Okay. And now what is L d dy of dx? 0? Yeah, how do you get 0? Yeah, d and L commute, right? So this is d L d dy of x. And the derivative, the Lie derivative of a function is the usual derivative. So this is dx dy, and d of 0. So it's 0. Okay? Yeah. And what about L d dy of dy? Yeah, because it's d of L d dy of y, and so that's d of dy dy. This time is d of 1, but d of a constant is 0. Okay? So these two terms are 0, and this is going to be dg dy dy. Okay. Okay, now, if you have the first condition, if it has no dy term, then G is 0. Okay. So you're left with this. So this is df dy dx if there's no dy term. So if G is 0. Okay. And yeah, and so the second condition is that f does not depend on y. So f is a function of x alone, and in that case, this will be 0. Okay? Yeah. So you see, I can. So now I have this result. Let me see. So proposition omega equals f dx plus g dy, which is a one form on R2, is basic for this principal bundle if and only if the interior multiplication is 0. So that says G is 0. And to say that f does not depend on y is equivalent to saying now that the Lie derivative is 0. Okay? Yeah. So for this particular principal bundle, we have a very simple condition for a form to be basic, for one form to be basic. And now the problem is we want to generalize this condition to an arbitrary principal bundle. Okay? Generalize this proposition to an arbitrary principal D bundle. Mm-hmm. Yeah.
So we should replace part of y at some, for example, 垂直微分跟水平微分这种分法。
Yeah. So we have to replace ddy by something. But what is so special about ddy in this example? Yeah, ddy is a vertical vector. Okay? So on any principal bundle, we can define vertical vectors. Right? Vertical vectors are vectors that projects to 0. So let's first make that definition. Mm-hmm. So yeah, we have to replace that by vertical vectors. Yeah, actually, it's going to turn out to be just that. Well, actually, now, yeah. And then we have to, yeah, actually, that's how we generalize. Just replace ddy by vertical vectors, and then it's the same condition. Okay, now, so, yeah. So vertical vectors on a principal bundle. Okay? Actually, you can define. Oh, okay, yeah, let's just stick with principal bundles. I think the definition makes sense for in any fiber bundle. But let pi from P to M be a principal G bundle. Okay? And P is a point in P. Okay? Then the differential at P maps the tangent space at P to the tangent space at pi of P. And the vertical vectors are the kernel of this map. Okay? So definition, VP, these are the vertical tangent vectors at P. It's the kernel of pi lower star. Yeah. Okay. Now, whenever you have an action, okay, then an element of the Lie algebra of the group will generate a vector field. Okay? So let's look at an example. Okay? So let's see. So let's say we rotate the sphere. Rotate the sphere. Okay. So the circle, this is S1, acts on S2, and the circle is a Lie group. Here's the identity, okay, and so this is a tangent vector to the identity. Therefore, yeah, it's an element of the Lie algebra. This is the Lie algebra, this line. Now, this vector, it gives you a curve on the circle, so let's call it X, A. So an element A in the Lie algebra gives a curve by the exponential map, e to the TA, in the Lie group. And then if you have a point, any point P, then e to the TA P is a curve in M. Okay? M is S2 here. And so it has an initial vector. Okay? So every point, once you pick an element of the Lie algebra, right, every point will give you a tangent vector to the manifold. And so you get a vector field. And the vector field will look like this, right? Because the orbit of a point are horizontal circles. Okay? So this is called a fundamental vector field. Okay? So every element of the Lie algebra will give you a fundamental vector field. So I'm going to now define a fundamental vector field of an action. So if G acts on M, let's always assume that it's smooth. And A is an element of the Lie algebra of G. Then the fundamental vector field is denoted A bar. So A bar at P, so for each point P in M, okay, I make this definition. A bar at P is this curve e to the ta dot P, and then you take its initial vector. That means you differentiate with respect to t and evaluate at t equal to 0. However, now the action can be on the right or on the left. Okay? And if it's on the right, okay, yeah. So, just a minute, yeah. Well, here I have written it on the left. So if G acts on M smoothly on the left, say I make that definition. But if G acts smooth on M on the right, then I have to write it on the right. I have to write the group element on the right. However, you see, a right action can be turned into a left action, right? But when you turn it into a left action, then you need to take the inverse so that it will remain an action, okay? So you can't have these two because this right action, if you turn it into a left action, it actually has a minus sign. Okay. This is equal to this, okay? So if you have a left action, we will put a minus sign there. And if we have a right action, then there's no minus sign. Okay? To be consistent, then these are equal. Okay? Yeah. Also, you need this minus sign because later you will have a theorem that says that if you take two elements of the Lie algebra, you take their bracket, and then you form their fundamental vector field. It turns out that this operation is a Lie algebra homomorphism. So this is equal to A bar bracket B bar. Okay? So, if you have a minus sign. If in this definition you don't have a minus sign, then there will be a minus sign here. Okay? So, so you want to put the minus sign there and not here, okay? In order to get this. Okay, so that's a fundamental vector field. Now let's write down some properties of the fundamental vector field. So theorem. Okay, that's one property for AB in the Lie algebra. These two brackets are different brackets, right? This bracket is the bracket in the Lie algebra. This bracket is the bracket of vector fields on the manifold, okay? Well, the first theorem is that, you see, now as you vary P, you get a vector field, and that vector field is C infinity. Okay? So Yeah, I'm not going to prove it here. Okay, it's done in the book. You basically, you apply this vector field to a C infinity function, and you see that you get a C infinity function because all the operations are C infinity, you know. And then next, I want to write down the integral curve of this vector field, because I now have a vector field, a C infinity vector field on M. So it has an integral curve. So if I fix a point P, the integral curve of this vector field through P in M is phi t of P is equal to, it's actually this e to the minus ta dot P. Okay? You see, this only says that the derivative at 0 is the vector field at P. Now, to be an integral curve, you have to have the derivative at all time t. Okay? So, we need to show that the derivative at all time t is the vector field at the point at time t for all t. Okay? We only know it for t equal to 0. But we need to have it for all t. So we just go ahead and calculate this derivative. I'm going to say let phi of t p be equal to e to the minus ta dot p. Okay? I define phi t by that formula, and I want to show that it's an integral curve. So I need to calculate its derivative. And now the derivative at time t is obtained by moving t a little bit, right? So you add s to t, and then you differentiate with respect to s at time 0. Right? That's the derivative at time t. You move t a little bit and differentiate. And this is dds of e to the minus t. Oh, sorry, there's an a here. I forgot the a. But the exponential has the property that this is e to the minus ta, e to the minus sa, e to the minus ta, right? Yeah, the exponential has that property. P, okay? And then we evaluate s equal to 0. Okay? And so now this is our new point. So we are multiplying the new point by e to the minus sa, differentiate and evaluate s equal to 0. And so that's going to give us a bar, but at the new point, e to the minus ta dot p. And this is a bar at phi t of p. Okay. So that says that phi t of p has velocity equal to the vector field at that point. Therefore, it is the integral curve. Okay? Yeah. So you can also say the integral curve phi t is left multiplication by e to the minus ta. Yeah. Okay. Yeah. Okay. Now, if you have a principal bundle, then the group acts on the total space P. So what do the fundamental vector fields look like? Yeah. So if I from P to M is a principal G bundle, then G acts freely on the right on P. So a point, so the curves will all be along the fiber, see? So the fundamental vector field will consist of vertical vectors. Yeah. And AP is a vertical vector. Okay. Yeah. See, there's another way to get AP. So, fix P in P and define JP from the group into P by sending G to P dot G. Then the differential from the identity, which is the Lie algebra, to T P P is given by, okay, so the differential of JP of A, the way you calculate the differential is that you take a curve, e to the TA, that has initial vector A, and then you apply it, you map it over. So you map it over, and then you differentiate at t equal to 0, right? That's how you calculate the differential. But you see that this is equal to ddt at t equal to 0 of p dot e to the ta, okay? And that's precisely the definition of A bar p. So A bar p can also be calculated as a differential of JP. And then if you take the pi lower star, okay, if you take pi lower star of A bar P, you see that it's pi lower star of JP lower star of A, and that's my functoriality, pi composed with JP lower star A. Okay? But what is pi composed with JP? This is JP. Yeah, it's just a constant P, right? Okay. This is the constant map P. So the differential is 0. Okay?
Is that constant map pi p? Constant map pi p?
The constant map, let me see. Sorry. Yeah, pi p. Yeah. Right. It maps to pi of p. Good. Yeah. Pi of p. Yeah. I'm really glad that you are awake. You know. Yeah. Sometimes I teach, and I make mistakes, but nobody catches me. In the United States. But here, I see that you are always awake. You always catch me. Very good. Yeah. You see, I'm afraid to watch myself on YouTube, because I'm afraid that I will see all those mistakes. But hopefully not, because I hope that you are all awake, and whenever I make a mistake, you catch me so that it will forever be correct. Yeah. Yeah. Okay, so this is like a more, what do you say? Yeah. Watertight proof that A is a vertical vector field. Now, all right. So next I want to talk about invariant forms. Invariant forms and how to characterize invariant forms. Well, you see, if you have a basic form, okay, so invariant form, then it's going to be invariant. So a basic form on P for a principal bundle, a basic form, it is the pullback of something from the base is pi star of omega for some omega in the base. And that means if you apply, so you have G acts on the right, on the principal bundle. So RG star of pi star of omega, right? This is going to be, now pullback is contravariant, so this is going to be pi composed with RG star of omega, okay? And what's pi composed with RG? It's still pi, right? Because RG stays in the same fiber. So, yeah, pi of RG of any P is pi of PG and that's the same as pi of p. So pi composed with Rg is pi. Okay? And this says that a basic form is invariant under right translation. Okay? So if in general, I can define invariant forms on a G manifold. So definition, if G acts on M, usually we look at left actions on the left, then omega in M is invariant if LG star omega is equal to omega for all G in G. Okay? And if it acts on the right, then you would use RG star. Okay? And so what we can say is that a basic form is invariant, is G invariant. This is G invariant. So the basic form on P for a principal bundle is G invariant. Okay? So that's a necessary condition, for a form to be basic. It has to be G invariant. And therefore, we would like to characterize G invariant forms using the Lie algebra. And this only works for G connected. You see, the Lie algebra, it is the tangent space at the identity of a Lie group. So it does not see other components of the Lie group. See, if the Lie group has many components, the Lie algebra only sees the component of the identity. Okay? So if you're going to make a theorem about the Lie algebra, you have to assume that G is connected. Then omega, assume that G is connected and acts on M. Then omega is G invariant if and only if the Lie derivative is 0 with respect to the fundamental vector field A, okay, for all A in the Lie algebra of G. Now, in one direction, this is kind of obvious, because if omega is G invariant, then e to the minus ta, just a minute, then Lg star of omega is equal to omega for all G in G. So this implies that L of e to the ta star of omega, or L of minus ta star omega is omega for all a in G, okay? Now this only goes in one direction, right? Because these are just some of the elements of the group. And, but you know that this left multiplication by e to the minus ta, it was the integral curve, dt. And so this is the same as phi t star of omega. And the Lie derivative with respect to A, okay, it's the differential at time 0 of the pullback by the integral curve of A bar. And so this is ddt of a constant, and therefore it's 0. Okay? Yeah. So in one direction, it's pretty obvious. Now, in the other direction, yeah, it's a little bit trickier, but I think my time is up, so I'm going to stop here. Okay, yeah, all right. Okay, good. Yeah, we'll finish it next time. All right. Yeah. So I skip over a few sections, and I will be sending you chapter 3, okay, later today. And it has all of this. But I'm not going to do everything in chapter 3. We can skip over a few sections. Yeah. Okay.